Alright, so today I'm going to be explaining this important paper with the title Fast Three-Field Integrators from Low Displacement Rank to Topological Transformers. So this paper in 2024 by Google DeepMind and Google Research. We present a new class of fast polylog linear algorithm based on the theory of structured matrices, in particular low displacement rank for integrating tensor fields defined on weighted trees. Several applications of the resulting fast three-field integrators are presented, including approximation of graph metrics with tree metrics, graph classification, modeling on meshes, and finally topological transformers for images. For topological transformers, we propose new relative position encoding masking mechanism with as few as 3 extra learnable parameters per transformer layer, leading to 1 to 1.5% plus accuracy gains. Importantly, most of these are exact methods, thus numerically equivalent to their brute force counterparts. When applied to graphs with thousands of nodes, those exact algorithms provide 5 to 13 times speedups. So even in the previous video, I talked about these topological transformer masking of that. But now here we have a different version of that, different idea. So we refer to f-distance matrices which play an important role in several machine learning algorithms. And we consider a matrix M. Now this distance here, distance stands for shortest path distance between any two vertices of an indirected graph like I and J. It's very similar to the idea of a previous video, but from a different perspective. We call M a f-distance matrix, and M is the shortest path kernel matrix. And the product represents a scalar field on V obtained by discretely integrating the field defined by X. In this integration, a new field value at the vertex V is calculated by averaging the all field values at all vertices U, weighted according to the function f of distance of V and U. This integration can be extended to general tensor fields by replacing vector X with a tensor. So we highlight several applications that rely on multiplications with f-distance matrix, interpolation on manifolds, optimal transport, and topological transformers. So we provide the first exact polylog linear multiplication algorithm called FTFIS. Applying tree metrics to compute approximate M is a natural approach to scale up matrix multiplication. If a tree metric approximates the metric space well, then the derived embeddings should have low distortion. I've explained all of these in my playlist for metric embedding. However, in the worst case scenario, this is not true for deterministic tree embeddings. A natural alternative is to sample trees from probabilistic distributions, which are shown to provide logarithmic distortion in expectation. You see this pictorial representation of integrator tree, that the data structure for the 9-vertex input tree on the left. Numbers in the blue next to input tree denote the weights of its edges. Leaves of the integrator tree object represent F-transformed distance matrices. different levels correspond to different distances from the pivot point. This is the pivot point. So level 0, level 1, level 2, level 0. So to support fast integration for various tensor fields defined on a given input tree, we first design a special data structure that referred to as an integrator tree. An object of this type is constructed only once per tree. So it has a pivoting property. If K is a tree, then K admits a decomposition. And it can be constructed in linear time. Now, integrating with integrated trees, we are ready to explain how ITs allow us to efficiently integrate any given tensor field for a wide class of functions. We will apply divide and conquer strategy. We start in the root node of IT. If node is a leaf, then the F transport distance matrix is stored and can be directly used for matrix tensor multiplication. If this node is not a leaf, then it encodes the decomposition. To compute new values of field for nodes, one needs to compute the contribution to it from the left tree. This can be done simply by applying equation 2 recursively. The key observation is that the latter, which the cross term contributes, can be this one, the cross term, can be retrieved simply by computing the Cx prime. So given the structure, the tensor x prime can be computed in linear time. Improving approximation quality with learnable F-distance matrices. We propose to further improve approximation of that model by learning F-distance matrix on metrics derived from the MST. As an application, we choose general graph metrics where our goal is to learn the shortest path distance between a given pair of nodes. Of course, I've seen a paper, they use transformer to calculate this shortest path distance between any pair of nodes. To evaluate the quality, we compute the relative Frobenius norm. And here T is a tree for a given graph, and ID is the identity function. Then we propose an extension to top VIT that seamlessly integrates FTFI. We scale our experiments to run on the larger VITL architecture and evaluate on ImageNet. So the output of this algorithm is the masked low-rank attention embedding using phi. This algorithm in this Kromansky paper that I've explained in a different video. And these phi are these kernel feature map. These are very important thing if you want to have a linear complexity for attention. There is a paper in 2019 called random feature attention, something like this, that they do similar idea. General mask attention is given by the following equation. Now M is the mask matrix, is the mask attention matrix. Similar to the previous video that we had a masked attention matrix. That we had, similar to a previous video, we had Hadamard product to the keys. if the kernel K admits a dot product decomposition, then you can write this as expectation of this kernel trick. Ali Rahimi burst in 2008 is very important. You see it everywhere. So these are data sets like MUTOG enzymes, NCI1 for graph classification, which are very important. Enzyme is the hardest one, maybe because it's not balanced or some problems with that.